Alright, enough about my Clemenza recipe. What we're going to do now, this is the lecture that I would have had with you on, just to make sure that we're all in the same time frame, April 8th, Wednesday, April 8th, 2020. Now that we have the backstory of where the energy in a molecule, be it a carbohydrate or a lipid, actually comes from. It comes from the delta G, the positive delta G, when electrons fall from high to low energy orbitals. Let's take a look at food and how your body, in particular your cells, take food and turn it into useful biological energy. And we'll start the story, if you will, with a single molecule of glucose. Let's see what my next slide is here. Yeah. A single molecule of glucose, of course, would come from this bowl of pasta. This bowl of pasta is amylose, remember, starch. And there are a gazillion molecules of glucose in this small bowl of pasta. We're going to take one of those molecules of glucose and follow its fate through the entire metabolic process. In other words, we're going to follow the fate of the piano as it goes down those 3 flights of stairs that I mentioned before. First glycolysis, then the Krebs cycle, otherwise also known as the Krebs citric acid cycle, and finally the electron transport system. And given the fact that there aren't going to be any questions, and I don't have any, I won't be taking time out for any thoughts, musings, or questions. I probably will get through the entire metabolic process in this one sitting. That doesn't necessarily mean you have to listen to this entire video in one sitting. You can digest parts of it, and assimilate it in 2 or 3 pieces. Because, admittedly, there's going to be a lot of information coming at you in this hour and 10 or 15 minutes. So there we are. We have a bowl of pasta. You eat the pasta, you chew it, otherwise known as masticating it. Your saliva already goes to work on the pasta even before you swallow it. In a complex carbohydrate such as amylose, your saliva already breaks down that amylose to disaccharide units for the most part. That is, as long as you chew the way your grandmother told you to chew. I forget what the number of chews was, but my grandmother sat at the table with us and told us how many times we're supposed to chew our food. Anyway, and by the time you swallow it, this amylose has been broken down to units of 2 glucose molecules joined together. Not the tens of thousands of glucose molecules that are in one piece of spaghetti, but 2 glucose molecules. So they get to your intestine already almost down to 1 glucose molecule, and by the time the stomach gets through with that, and they get into your small intestine, you're down to 1 glucose molecule, which is absorbed through the intestinal wall and gets into your blood. That glucose molecule then goes to some muscle cell that you're going to use to go ride your bicycle, work out, walk to school, do whatever, get up from the breakfast table and do whatever you need to do to carry on with your daily activities. That muscle cell is going to take that 1 molecule of glucose and do this with it. It's going to take the glucose through glycolysis, the first of those 3 metabolic staircases that I keep referring to. Let me adjust this a little bit here. I don't know how to make that bigger. If I can make that bigger, I'm just going to have to move it up and down a little bit here. All right, so we'll start at the top, which I believe you can see now. Here's the molecule of glucose that we've just started with, that your muscle cell has taken up and is now going to metabolize in order to get the energy out of it so that it can contract. The first step of the process is an endergonic reaction. It's endergonic because, let's see what my next slide is. Okay. It's endergonic because ATP is being broken down to ADP. What is ATP? I don't have it up here. This is something I would normally write on the board, but you're going to have to bear with me for a moment because, I haven't updated this PowerPoint to do this online. If I ever have to do this again, I'll go through the PowerPoint, but there's limited time now. So here's what ATP is. You know adenine in DNA, adenine, cytosine, guanine, thymine? Well, ATP is related to adenine. The A in ATP actually stands for adenine. So without my writing it on the board, think of adenine, and it doesn't matter that you remember the structure of adenine. Just think of adenine with 3 phosphates attached to it. That's what the T means, triphosphate. ATP stands for adenine triphosphate. So think of adenine with this chain of 3 phosphates dangling off one side of the molecule. Okay? I'll give you a moment to, create that mental image in your head. Here's the thing. If a chemical process lobs one of those 3 phosphates off the adenine, the terminal phosphate off that chain of 3 phosphates, that reaction causes a lot of electrons to fall from high to low energy orbitals. What do you think is going to be the delta G? The delta G is a positive output of energy. It's like striking a match. It's like cracking a stick of dynamite, only not as catastrophic. It's just enough energy to carry this endergonic reaction, which requires energy to go from glucose to glucose 6-phosphate. Otherwise, it's not going to go. So this is the classic case of you want to make some money, first you have to pony up some money. You want to make some energy, first you have to pony up some energy. I got a little ahead of myself. First of all, you will not have to memorize any of this. Okay? You don't have to memorize all these intermediate compounds because they're not important. The intermediate compounds are just the steps of the stairs. They're intended to get by. The purpose is to get from glucose to pyruvate. In order to do so, we have to go through these intermediate steps. So you're not going to memorize any of this. I'm going to highlight, as I said, like taking a tour through, the Hollywood stars' homes, what I consider to be important about glycolysis for you. All right, that much I would ask that you remember. And I'll summarize at the end anyway. I'll make sure that you know what's important about this whole process after I've detailed it a little bit for you. So the first step, first of all, it's important that you remember we start with a molecule of glucose, and hang on to that. You start glycolysis with a molecule of glucose. The first step is an endergonic reaction, which will require an ATP. Put ATP on the back burner of your brain for a little while. We're going to see it again many times, but it's going to become very important at the end of this discussion when we finally get to the electron transport system. When I told you back when that glucose was the immediate source of biological energy, it was a white lie. But it was it was necessary, because if I had introduced it any other way, I would have had to go off on a very long tirade as to why it's not really the immediate source of energy. Glucose in your blood is like the checkbook in your back pocket if you walk into any general store in Vermont to buy something. Likely as not, they're not going to take your check. You have to have cash, or these days a debit card. But let's go back to the days of cash. You hand somebody around here a check, they're going to look at you and say, no, we don't take checks. You're going to have to go down to the bank and cash that check and bring us back the cash. It's the cash in your wallet That's the immediate source of energy. So the glucose is like the check in your back pocket, which you're going to have to cash in order to make the cash. The cash is the ATP. And in fact, many textbooks actually refer to ATP as the energy currency of the cell. So the analogy is quite accurate. So you're going to have to spend some coin, some immediate source of energy, in order to get from glucose to glucose 6-phosphate. If you're wondering where the ATP comes from, that's the whole point of the story. Just be patient. Nothing much goes on glucose 6-phosphate. It doesn't require much energy to go from glucose 6-phosphate to fructose 6-phosphate. It's a reaction that can go on with very little. It's probably an exergonic reaction, but there's not a lot of energy coming off of it, so we're not going to bother harvesting it. The third reaction of glycolysis is another endergonic reaction, we can tell, because another ATP is used. The terminal phosphate of ATP is taken off. The energy, the delta G that's released, is used to drive the reaction from fructose 6-phosphate to fructose 1,6-biphosphate. Right? In order for the reaction go from here to here, we have to have an input of energy. That input of energy comes from another ATP molecule. If you take the terminal phosphate off of adenosine triphosphate, what do you get? Adenosine diphosphate, ADP. That's what ADP stands for, adenosine diphosphate. 2 phosphates instead of 3. So you're probably bummed by now. We spent 2 coins already without having made any money, without having made any energy. The fourth reaction, quite obviously what happens at the fourth reaction is that the initial glucose molecule that we started with, by the way, I should have pointed this out in the beginning. These little 6 gray balls in the diagram represent the 6 carbon atoms of the glucose. I'm sorry. But that's what the 6 balls are. The very, very shorthand diagram of glucose for this purpose of this illustration. These little 6 balls represent the 6 carbons of glucose. So we can see here in the fourth reaction that the glucose is split evenly into 2 halves. 3 carbons here, 3 carbons there. So that what happens throughout the remainder of glycolysis happens twice. All the events that happen to one half of the glucose are identical to the events the reactions that happen to the other half of the glucose. So everything that happens, we essentially multiply by 2. In reaction number 5, NAD, and I'll tell you in a moment what NAD stands for, comes along and picks up, you see it right there, the H, a high energy electron riding piggyback on a hydrogen atom. Remember, hydrogen atom has 1 proton, 1 electron, 1 neutron. And when it picks up that high energy hydrogen atom, it takes that high energy electron with it, which means that the electron in the hydrogen that's being picked up, that's being plucked off of one half of the glucose molecule, is occupying an outer orbital. That's important to keep in mind. That electron is occupying an outer orbital. In fact, it had, in my analogy with the rock and the string, I was whipping that string around my forearm so hard that the rock broke the string and went flying off. But instead of flying off and putting out somebody's eye or busting a window, it got picked up. The energy of that high energy electron was picked up by the NAD molecule. I like to refer to the NAD molecule as a taxi cab that picks up a fare. And that fare is the high energy electron riding piggyback on a hydrogen atom. Alright? So stay with that analogy. And you should be wondering, well, where's it taking it? Where's it taking that high energy electron riding piggyback on a hydrogen atom? You're just going to have to wait. That's in an upcoming episode. For now, just remember that what's important is that this hydrogen is carrying a high energy electron.